Hey everybody, Dr. Data Science here, and welcome to the PyTorch Step-by-Step series, where we will cover everything you need to know about PyTorch, from the basics to advanced deep learning topics. All the code used in each video will be available on GitHub, and you will find the link in the description below. If you enjoy these videos, don't forget to like and subscribe for more content. Now let's dive right in. The first thing we want to do is import PyTorch, and the technical name is actually Torch. And then we can also check the version of PyTorch using this print option that we have here. So you will see that in this case, we have PyTorch version 2.3. So my recommendation is to make sure that the first number here is 2, so you're not using PyTorch version 1. And also here we have CUDA because we have a GPU available on this machine. So the goal here is to understand the basics of PyTorch by creating a simple neural network model for image classification. And a very important module inside PyTorch is this torch.nn, which is the core module for building neural networks. It provides a comprehensive set of classes and functions to define models, train, evaluate, you name it. And here's a breakdown of the key components that you need to know. So torch.nn includes containers such as sequential, if you want to construct feed-forward models by stacking layers in a sequential manner, or you can use also the module, which is the base class for all neural network models. In this video, we use sequential because it's a little bit easier, but obviously module is a lot more powerful. Another thing that you need to know about this torch.nn is also the way that we can access different types of layers in neural networks, including linear layers, convolution, recurrent layers, transformer layers. So you can see that we have access to all sorts of layers that we need to build neural network models. We also can access built-in activation functions such as ReLU, or exponential linear unit and many other activation functions. And also we have access to loss function. So you see that in this case, because we are using a classification problem, we need to use the cross entropy loss function, and that's something already available within torch.nn. Another thing that we need to know about PyTorch is that the way that we can create a data set and feed that to the model is different from other libraries, including TensorFlow and Keras, in a sense that it's a little bit more object-oriented way, meaning that we have two important modules, one data set and the other one data loader, which we can import them through torch.utils.data, right? So we always want to use this torch.utils.data, and we import data set and data loader. So data set is an abstract class just representing a data set. And the nice thing is that it allows you to uniformly load and process your data. So that's something that is very useful if you want to have a custom data set or even use a standard data set that are already available within PyTorch. But one thing that we always also need to remember to use is this data loader. So data loader is a class that wraps around this data set to create an iterable, right? So remember when we talk about neural networks and deep learning models, the way we train them is we provide batches of data, and the way that we can create these batches is using data loader. So that's something that is very important here, to create batches, shuffle them, or do other things that we need for training purposes, because in general, we are not able to provide the entire data for training a neural network model when we have very large data sets. But the most important thing that you need to know about data loader is grouping data into batches of a specified size, right? That's why it's known as batch size. Okay, so now that we know the motivation behind most of these things that we are importing here. So we are importing torch.nn as nn, so we don't have to use the full name anymore. This is the alias. From torch.utils.data, we import data set and data loader. We technically don't need data set here because we are using a built-in data set in Torch region, but we definitely need data loader. And also we need an optimization technique for implementing gradient descent, and that's through torch.optim, right? So that's inside torch.optim and not torch.nn. That's something to keep in mind. So we're going to run this cell. Everything is okay now. So since we are working with image data sets here in this video, we need to also learn how to transform these images, meaning that you will see soon that the image that we have here is in a format called PIL or PIL, Python Image Library, whereas in PyTorch, we want to work with tensors. So we have to, get this image and create a tensor. And the way that we can do this is using torch region.transforms, and we use v2, which is an extension of the original torch region.transforms. And this allows us for, advanced data augmentation and pre-processing techniques for especially images, including resizing, normalizing, flipping images, and creating tensors, etc. So in this case, we mainly use in this cell for image data sets. So we're going to import torch region. We're going to import torch region.transforms.v2 as transforms. Also, we need to use this functional from torch region transforms, which you can think of this, really as the name suggests, is like a function that we can apply, for example, to create tensors. And we also import matplotlib for visualization purposes. Before we really dive into these specific details, I would also like to tell you about model agnostic code in PyTorch. So depending whether you have access to GPU or not, one thing that you can do is that you can use this torch.cuda that is available to make sure that you actually have a GPU and you correctly install CUDA to be able to utilize your GPU. And you can see that here is true, meaning that we have access to that. So you can write your code in model agnostic form. So meaning that if torch.cuda that is available is true, then the device that we want to use is CUDA, and otherwise is CPU. And so the nice thing with this kind of like conditioning here is that if you have, like, let's say only access to CPU, still your code will work and this device will be set to CPU. And if you have GPU, they will be set to CUDA. And so you can see that when we print device, we get CUDA, and because this is, in this case, we have GPU. So in the rest of this notebook, we're going to focus on 3 parts: preparing data using dataset data loader, defining and compiling the model using torch.nn, and then writing like 2 for loops, one for training and then one for evaluation purposes, right? So for one, we use training data, and for evaluation, we need to use some holdout or test data. So let's look at preparing data. In this case, we're using a built-in data set, which is available in torch region.datasets. Here's the link. There's actually a very nice list of region data sets. And one of them is MNIST data set, right? So these are the handwritten digits that we have. And the way you can access these is by creating a route or path that you can use to store the data, and also mentioning whether the train is set to true or false. So for training data, train is true. For validation or testing data, the train option is set to false. And obviously, we want to download these. So you can see that in my case, this is much faster because I do have this thing downloaded. So you can see it here that I have this data set already downloaded. Okay, so what's inside this thing? So here's the thing, right? These are not just tensors. We have a lot more information. You can see that this train set, right, it has 60,000 data points, right? So 10 digits, 6,000 samples per class. And this is for the training purposes. You can look at the validation. So here we have 10,000. So we know that for MNIST data set, you have a total of 70,000 data points that we have divided them into 2 groups, one for training and one for validation. But what's inside this thing? So look, for the train set, we know there are 60,000 data points or elements. Let's look at the first one. And if I run this, you can see that this is actually a tuple because we have these parentheses. The first one, again, is an image, this PIL image that I said, Python image library. And we have this number here, 5. So it is easy to guess that this is the label or the digit that that image is representing. So we can use this unpacking to separate the image and label. So now if I run this cell, you can see that that's digit 5, right? And of course, computers don't know exactly what this represents. They just look at this as a 28 by 28 array. But if we, and this is the type of it because it's an image, right? But if I look at the label, you can see that now the label is 5, right? So we have this image here, and we have this label, and we want to train a neural network model that we can fit these images and get these labels from the model. And again, I would like to emphasize that this pill is essentially a Python object that encapsulates all information and properties related to an image. So that's very common to use when you have any type of image processing. And for this label, this looks like an integer, but you can always use type anywhere in Python to find the type of the object, and this is an integer. So that's great. The last thing that we want to do here, which is very important in terms of pre-processing, is being able to get this pill image and create this to a tensor, right? So in this case, we can use from the functional that I mentioned, we imported this as f, we are using 2_tensor, right? So this means that you convert a given image in the form of a pill image in general, and you create a PyTorch tensor. So that's great. Let's see if this works or not. So we have f.2tensor. This is the pill image that we had before. And now I call this image tensor after the conversion. And if you look at the type, you see that this is indeed a torch tensor, which is great. That's what we need in order to be able to fit this into a neural network defined inside PyTorch. And in order to make this more, I would say, principled and efficient, one thing that you can do is inside transforms, there's this thing called compose, which means that you can create a pipeline, a series of transformations. In this case, we don't want to manipulate the data very much. The only thing we want to do is to create tensors from these pill images. And for this, we use the lambda function. So we create this lambda. This is the keyword. So the input is image, and each image will be sort of like fed into this functional.2tensor. So this means that get each pill image and create a PyTorch tensor, and that's the main transformation that we want to do. And I call this TRN, right? So that's like the transformation that we have. So if I, for example, give as an input argument image to TRN, you can see that we get the torch.tensor. And the nice thing is that once we do this, also we do normalization, meaning that now the maximum element or value of each tensor is 1 and the minimum is 0. So this is a very common thing to do when you're working with any kind of image data, to make sure that the pixel values are always between 0 to 1. And if you look at the shape in this case, you can see that this is 1 by 28 by 28. Something important to know about PyTorch, the way that we represent images, is through this 3-dimensional tensor or array of size, channel, height, and width. And if you have a color or RGB image, you have 3 channels, right? RGB, red, green, and blue. And if you have a grayscale image, you only have 1 channel. And now we can use plt.imshow to plot this image, right? That's what this IM here stands for. The only thing to know is that, if you just give this image tensor, you will get an error because it's a 3-dimensional array. So the only way to really, fix this problem is to get rid of this, first axis, which is always 1. So it doesn't really have much information, and that's what we use using this squeeze, right? So this will automatically, squeeze this 1, so it means that the result would be 28 by 28, and the color map is obviously gray. Okay, so this is that 28 by 28 image that we got from the pill image and convert this to a PyTorch tensor. And in order to make sure that you apply this to all the data points that we have, so if you remember, we had train set and validation set, there is an attribute called transform, and you set this equal to TRN that we define. So this means that from now on, when we work with this training set and validation set, we are going to apply that transformation that we define, which is mainly just converting everything to a PyTorch tensor. Okay, so now let's not forget to run this, and this is the part that is very important. So in order to be able to provide this data into, divide this data into batches and provide this to, during the training process, in one batch by one batch, we need to use this data loader, right? So this data loader, we need to use once for the training, one time for validation. The main thing you want to use is batch size. So we want to make sure that in both cases, we use this batch size 32. And we set the shuffle equals true for training. And the reason is that at the beginning of every epoch, so one epoch means one time we go through the entire data, we want to make sure that we shuffle the data, right? We change the order of the data, so we are not always going through the data with the same order. So that kind of like helps in terms of convergence and usually like generalization performance. So now we know about data set and data loader. That was the first part of this video. In the second part, we want to define and compile a model, right? So one of the most important thing to know here is that we have this 28 by 28 tensor, and we want to make this a one-dimensional tensor, or in other words, we want to flatten this tensor. So inside that torch.nn that we imported as nn, there's this flatten layer that does this. In order to see this, we create this tensor, right, of I can just run it so you can see it, right? Which contains 1, 2, 3, and 4, 5, 6. So that's our original tensor. The size of this is 1 by 2 by 3, right? So the first axis is 1. And if we fit this to the flatten layer, as we expect, you can see that now we have the first row, and then the second row is added to the first row. So now it's a one-dimensional sort of like representation of these two-dimensional data, right? And the first axis always is 1 because that's technically the batch size. So that's kind of like important to remember that the way that we feed data to in this case to like a neural network model, the first element is the batch size, and in this case is 1 in general because we set the batch size to 32. Later on, it's gonna be 32. And then we have the channel, and then we have height, and then width. Okay, so now we want to define the layers for our model. So the first layer, again, should be a flattened layer, meaning that we get this 28 by 28 image, and we have only one channel. And now we have something of size 1 by 28 by 28, which is, if you do the math, it's 784 elements. Now the next thing is to create a linear layer. So to create this nn.Linear that connects this 784 neurons to another set of neurons, and that's what is called the hidden layer. And in this case, we assume that we have 512 neurons there. So this is something that we have to specify, and you can obviously change this as you want. And once we do this, remember in neural network, we have this linear transformation, and then we have some nonlinear activation function. And for that, we use rectify linear unit. So in this case, if I print layers, you see that we have flatten. As it says here, it starts this flatten starts applying this transformation to flatten or vectorize everything from the second dimension, because indexing it starts from 0. So this is technically second. And again, the idea is that you always have something of this size, batch size, number of channels, height, and width. So what you really want to do, you want to have batch size and then everything else to be flattened or vectorized. So that's channel, height, width, which in this case is 1, 28, 28. The other thing is that I added full description here, so you can always read this text here, and that should really help you. Okay, so now we want to complete this, right? So these 3 layers are what we just talked about. Now let's say we want to also add another hidden layer. So we have another hidden layer with 512 elements or neurons in it, and we use another activation function. And you can always print this to make sure that this is working the way that you expect, right? So it gives a lot of information in terms of this is a linear layer, input features. We have 784, output is 512, and the same thing for the other one, from 512 to 512. And now let's complete this neural network, right? So this is what we already covered. And then in the final layer, because we have a classification problem and we have 10 digits, we have this n classes equals to 10, and we use this linear layer. And so now in order to create our network, what we really need to do is use this nn.Sequential. And this means that now we want to use a feed-forward network that we, stack together all these layers in a sequential manner. And the way you do this is that if you just provide this list or Python list that we have called layers, you get an error because you really have to unpack this or open this. And there's a trick in Python which is very useful, and using the asterisk right before your list. So this is what is called an operation called unpacking, which takes all the elements in the list and unpacks them. So it tells this nn.Sequential, use this nn.Flatten, nn.Linear. So this will allow, a nice way of unpacking all the layers that we have inside this layers list. And here you can see that, right? We have a sequential model. We have technically, 6 layers with flatten, and then the first hidden layer, the second, and then the output layer. One thing that you need to do, because our code is model agnostic, is to send this model to the device, right? So we send it to device, right? And so you can see that now we have everything on the GPU that we have. And something that has been added to the version 2 of PyTorch is that you can also compile your model, and this will accelerate model training and inference by optimizing a lot of operations under the hood. So that's definitely, I would say, something you want to do if you are using PyTorch version 2.0 and later. So in this case, that's what we have. And then the third part is training and evaluating our model. Okay, so when you want to do training, one of the most things is to define a loss function. And a loss function is what measures the disagreement between true and predicted values. And since you're using classification again here, we use the cross entropy loss, which is part of that torch.nn, as we promised. And the nice thing about this is that this also automatically applies the softmax layer, right? So this means that you do not need to put a softmax activation for your last layer because it automatically does that for us. And also, the negative log likelihood, which is the actual cross entropy loss function. So therefore, in this case, we define our loss function, right? So this means that our loss function accepts two things: the predicted logits, or what our model predicts in this case, and then the true labels. We also need to have our optimizer here to be able to reduce the value of this loss function. We use the atom optimization technique, and you have to pass all the parameters of your model so you know what you're updating. And that's what this model.parameters is, right? So it gives you all the parameters. And you can even list it here. So if you convert this model.parameters to a Python list, you will see that these are all those weight matrices that you have that takes you from one layer to the next layer, right? And these things are filled in with values right now because you always initialize these weight matrices randomly, right? So there are some values here. Probably right now this is a really bad model because these weights have not been optimized, but you will see what we have inside these model.parameters. And the next thing you need to do is to be able to evaluate the accuracy of your model, which is the number of correct predictions. So one thing you need to know is that how many training data points you have, how many validation data points you have. And that's relatively easy to do. We can, just check the length of the data. And now we need to write a function to measure the accuracy for each batch. Because remember, when you're working with neural networks, you always provide a batch at at one time. So that's a subset of your entire data. So in order to measure that, so we look at the logits or the output of the model. So this is before the softmax, the true labels, and the total number of data points or samples that we have. So for your logits, we need to figure out for each row where we have the maximum value, because that's where that data point belongs to. So we have this output.argmax. We have dim equals 1, so that means that it's row-wise, and we want to keep this dimension. So meaning that we don't want to reduce the one of the axes that we have in the data. And then after this is a very simple thing, right? Because this PRED or pred contains the digit number that we have, and we want to see whether this is equal to the true labels. And we can use this view as to make sure that we have exactly the same dimensions and axes so we can do the comparison. And then you count the total number of correct predictions, right? Because anytime you get a 1, that's a correct prediction. And you use .item to convert this PyTorch tensor to just a number. So you want to, extract that number. This is very important to use .item. And then you return this number of correct predictions over the total number of samples that you have. Okay, so let's run this. So now we are ready to write our training loop, and this is very important. So we have to keep track of two things: the loss and accuracy, right? Because you have cross entropy loss, and usually we want to know the classification accuracy. We put the model in the training mode, right? So that's model.train. That's important if you use some special layers like dropout. And now this is the main part. So you write a for loop to go through that train loader, right? So remember, train loader was what we got using data loader, which you have these different batches. And so at every epoch, we have to go through all these batches. You first send your data into the GPU, right? So this is important if you have a GPU with limited memory. You don't want to send everything there. So we send just what we need. Then we send the input, which are these images to the model, get the logits or the values of the 10 nodes that we have. And it is important always to make sure that we zero out the gradients from previous step to prevent accumulation. That's how PyTorch is. So you need to make sure in this case for feed-forward neural networks to use this zero grad. And then we evaluate the value of the loss function for that batch. So that's what we call that batch slice. And that's the logits and true labels. And then you use dot backward to find those gradients. And once you find gradients, now use optimizer.step to be able to update the model parameters using gradient descent, which here we use add. So remember that we want to keep track of all the loss values. So we look at this value of loss that we have for this batch, add it to the loss. And similarly for the accuracy, we're going to look at the accuracy for this batch and add it to the total accuracy. And at the end, we can print these things using dot format. So we print the value of loss and accuracy at the end of this for loop, right? So this is not inside the for loop, it's right after that. And we have a similar thing for validation or testing part, but except the fact that here we don't want to update model parameters. So it's a little bit easier. We still have to keep track of loss and accuracy. We put the model in the evaluation mode. We want to make sure that we are not messing with the gradient. So we use torch.nograd, right? And then we go through the valid loader. And in this case, we send the data to the device. So that's, whether it's CPU or GPU, and also, find the value of the output for the input and measure the loss function and accuracy and print them once we are done. Right. So now let's say that we want to have 5 epochs, meaning that we want to go through the entire data 5 times. So we write a for loop for going through these epochs. We print the epoch number, and we run the training loop and validation loop that we have. And so this will take a little bit of time because, of course, we have to send the data to the GPU and, go through the entire for loop because we have, like, let's say 60,000 data points. And each epoch, we have to divide this into batches of size 32. So you can do the math to see the number of times that you actually have to update model parameters. So you can see that we start to see results, loss function value for the first epoch on the training data is 300. And then for the validation data, the accuracy already is pretty good, right? So it's more than 90%, but you will see that it's getting better too. So we are waiting here to actually get the results for all the 5 epochs. I want to show you how much this will take time on the GPU that we have here. So you'll see that we got the result and we have a model, which is about like 98% accurate. So this is not the best accuracy you can get using, this MNIST data set. But the nice thing is that this is a pretty simple neural network model and we are not using any convolutional layers, and that will be the topic of a future video. So now let's see how good or bad this model is by just looking at one image. So remember we had that image tensor that we defined earlier, which was this digit 5. And let's just send these to the device, which here is GPU, and see what the output of our model is. So as we said earlier, our model here creates 10 values because we have 10 nodes or neurons in the last layer. And the way that this works is that we're going to look at the maximum value because that means that it's the most likely class that that data point belongs to. And it's obviously this one. It might be a little bit hard to right now count, but you can obviously use that argmax with dim equals 1, meaning that we want to go through axis 1 or row-wise. And in this case, you see that the result is digit 5. So you can see that this neural network model that we have now can correctly identify the class for this data point.